Hello, everyone. My name is Elisa Baum, and I am GridGain Systems Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. First, could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? Let's see, do I see hands? Hands. Oh, great. Okay. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible. And in addition, a recording of this webinar will be made available to everyone within 48 hours. Now a brief introduction to today's speaker. Today's webinar, Redis Replaced, Why Companies Now Choose Apache Ignite, is being presented by Dennis Magda, who is our Director of Product Management at GridGain Systems, but also Apache Ignite PMC Chair. For those of you who are not familiar with GridGain Systems, we are the company that originally contributed the code to the Apache Ignite project, and I'm the leading contributor of the project today. We also provide the only commercially supported release of Ignite, along with security, deployment, monitoring, and management capabilities, global support, and services. I'd also like to introduce Rob Meyer. He is GridGain Senior Director of Outbound Product Management, and he'll be joining us for the question section of this presentation. So with that said, I'd like to turn the floor over to Dennis. Go ahead, Dennis.
Thanks, Alisa, for the introduction. Hello, everyone. And thanks again for coming to our webinars. Those of you who have attended my webinars before, today, guys, we can take a rest, we can relax, because we are not going to look into the technical details of Apache Ignite or other distributed systems. We would rather today step aside and take a look at the timeline of how caching technologies evolved over the time. We are going to see what happened in the hardware market. We are going to see how our market came to the situation when now the market is flooded by many different distributed caches, data grids, and other memory technologies. Because there is always a reason, and today I want you to show the reason why the market is evolving and why the market is evolving in a specific direction. My talk is titled Redis Replaced, Why Companies Turn to Apache Ignite. And with this title, the whole point of this title is to emphasize that first, Redis is absolutely no doubts one of the most successful and honorable distributed caches in the market. It deserves to be named as the most valuable distributed cache that is used by many companies. But at the same time, it's not the end of the story. It's just one of the intermediate steps in the caching technology's evolution. And the second part of this talk just suggests that Apache Ignite also belongs to a specific part of the caching technology's evolution. Specifically, it belongs to the data grids and to in-memory computing platforms that followed Redis as a distributed cache. And having said this, we are going to look at this agenda today. We are going to walk through the different caching evolution timelines, specifically looking at hardware and operating system caching, finding out what hardware guys did to improve performance of operations, and what operating system developers included in Linux, Windows, or macOS to make sure that our applications can perform and benefit from being run on a specific operating system. Next, we are going to see how what happened at the application level, because having different caching technologies embedded into the hardware or operating system is not enough. And this is actually why we have many distributed caching approaches in the market today. We'll start with this, looking into the simple caching solutions that we used for a long time and still keep using as a part of our applications. Then we are going to see what happened with the market once it was disrupted by distributed caches, such as Memcached or Redis. But over the time, we also will find out that that was, again, one of the intermediate steps in the caching evolution. And the present most emerging technologies in the market that are related to the caching are data grids and in-memory computing platforms. And finally, once we finish with the caching evolution timeline, we are going to investigate Ignite from the caching capabilities perspective, because Ignite belongs to the final point on our caching evolution timeline in memory computing platforms, and I just want to show how it is different from the capabilities you can get in data grids or distributed caches offerings. And finally, again, I'll show you quickly quick and cool demo, and we will finalize our talk today with questions and answers. Okay, so let's move on and take a look at this caching timeline. But before we look at the involvement, I would like us to define cache term. According to Wikipedia, cache is a hardware or software component that stores data, so future requests for the data can be served faster. 2 points to mention here, or to pay attention to. First one, cache is not only about software. Today, we just accustomed to this term, relating it to different distributed caches or data grids. But at the same time, different caching techniques can be embedded even and to be a part of the hardware of our microcontrollers and CPUs. And final thing here is that the whole purpose of having a cache embedded into a hardware or software is to accelerate your request, is to accelerate your applications, to make sure that your applications can perform and execute faster by applying different caching techniques and technologies. And if to go to this caching timeline, actually that's my personal understanding. That's how I see the caching evolution over the time after working for GridGain and being a part of Apache Ignite community for a long time. So first, if to look at the hardware market, CPU caches appeared and became a part of integrated circuits around 1980s. This is when different vendors such as Intel, AMD, and started embedding different L1, L2, and L3 caches into the hardware. Then operating system vendors joined the game. For instance, around late 90s or early 200s, Linux Foundation and Linux community embedded different caching techniques such as page caching, buffer caching. They kept developing and modifying virtual memory architecture that exactly help us to use all the resources or all the physical resources much more efficiently in the later versions of these operating systems. Next, also around late 90s and early 200s, we as application developers started using different caching techniques for our services applications. That's actually what the time when the internet usage soared and when web applications disrupted the market. And for web applications, guys, you just need to recall that also we wanted to make sure that our requests as fast as possible, as efficient as possible. We wanted to optimize our web applications, and also we are going to see what we tended to use back at that time. And some of the techniques that were used back at that time are still widely adopted in current applications. But also those techniques and applications that were used by us in different services were not enough to cover all the demands. And this is why around mid 200s, the first distributed caches were developed and became available for architects and engineers. And here is we are going to talk and briefly cover the reason why they appeared, what were the benefits, what they solved, and we are going just to quickly walk through some of the major distributed caching techniques and products available in this segment. And finally, again, distributed caching technologies and products were not the final destination in this evolution timeline. All the time, the market welcomed other products that tend to optimize your applications by keeping data in memory. And here is we are going to talk about data grids and the memory computing platforms that combine all the best knowledge, all the best skills and all the best achievements of data grids in memory computing portfolio. So now let's zoom in and look into every specific point of this time, starting with hardware caching. So let's recall what was the problem and what was the reason why hardware developers decided to introduce different caches, embed them into our hardware. And here is the problem was that RAM is slow. Yes, it might sound weird for us, especially if we work with distributed caches that store data in RAM, but here is hardware guys try to solve another problem. RAM is extremely slow for CPU. CPU is such a fast part of our hardware, so that whenever CPU needs to obtain a new data or a new command that has to be executed by it, it has to go to RAM. And this round trip costs a lot in terms of CPU. Everything is relative for sure, but for CPU, every interaction with RAM is really expensive. And this is why in CPU we have another memory regions that are used by it to accelerate the performance of different applications and instructions and to make use of the CPUs much more efficiently. First, registers. All the data or all the commands that our CPUs are executing are stored in registers. Whatever you want to read or whatever you want to multiply, everything is going to be end up in the register first, and CPU is going to take a command or data from there. And it takes time, as we know, to get data or commands from RAM. And this is why hardware engineers added so-called L1, L2, or L3 caches. These are more dense but more performant memory regions that are usually integrated right into the CPU. And they actually behave the same way as software caches. CPU is going to cache there the most frequently used data, and whenever the cache is going to be exhausted, CPU is going to evict data from there and preload a new one from our main memory. Okay, so this is how the caches appeared initially in the hardware market. And this is how the caches could speed up interaction between CPU and main memory, just by introducing much more faster caches that were embedded into the CPU. Next thing that happened is that operating system vendors and developers joined this game. They also wanted to make sure that all the applications that work, let's say, on top of Linux can perform as fast as possible, and so that all the resources of your physical machine and your operating system can be utilized efficiently. And here is mostly operating system vendors try to solve another performance bottleneck. If hardware vendors saw RAM as a bottleneck for CPU operations, operating system vendors most frequently see disk as a bottleneck for input-output operations between your applications and disk. And this is actually why in many operating systems, including Linux, you can find so-called page cache or page buffer techniques. What's the idea about these techniques? If you take a look at the image on the slide, you can see here is our just commodity laptop that, let's say, runs some application, and this application reads or writes data from file A located on disk. And as we know that it can take a while from the operating system perspective to go to disk and to exchange blocks from disk and give them to your application. And this is why if you have enough RAM on your laptop, you can dedicate some RAM space to so-called page buffer that will cache some blocks of your file A right into the memory. And this will accelerate the read and write operations that go to this file. So your application, it will be transparent for your application. You will keep reading the data from file, and some of the data will be already located in RAM, and operating system will retrieve all the data from RAM directly. If you need to update something, first all this data will be again updated in page buffer, and later on it will be synced up to disk. So this is what's being done at the level of operating system. And similar techniques is applied for so-called memory mapped files. The memory mapped files are usually used when you as an application developer want to interact with your files as you would work with memory directly. You just create a file. The file can be fully located in RAM. If you want, it will be also persisted to disk. But these are the techniques that are embedded and available right now, I guess, in every major operating system. And those techniques that are eventually a part of virtual memory architecture of operating systems helped to boost input-output operations just by caching data in RAM, just by storing a copy of data in the main memory. Okay, so we have now different caching technologies applied at the level of operating systems. You know that depending on your CPU, you also might find different L1, L2, or L3 caches embedded, so that you can expect that your applications will run fast. But again, at the era of web technologies, at the era of the internet, they also faced the situation that it was not enough. Because if you take a look at this diagram to the right, you will find that there is some common application and some common interaction between some application and a end user. You have an application server with some logic deployed, and here we have the same our laptop that is working with our, let's say, a web application. And between our application server and our laptops, we have the network. And now the network becomes a bottleneck that we would like to solve. We want to be sure that if it's possible to, not to go to the application server just to retrieve a query result or frequently used data, I would just better take it from the local caches. And this is what we started doing back in late 90s or even earlier. We started using different local caching techniques. It might have looked like a local hash map that would take a result of your last operation and use the query as a key that will store a copy of this result in your local cache. And whenever you want to get and execute the same query, you just could get the result from your local cache. Or you can also, we could also cache different frequently used data. So there are many options and there are many use cases when developers and architects use local caches to avoid or to prevent expensive network round trips. And even if to talk about browsers, such as Chrome, Firefox, or Safari, those applications are also a good example of web applications that rely on different caching techniques a lot. They do not, whenever you just try to type anything, browser will make it hard, to go to a remote server only if it's needed. And it will try to use locally cached information as much as possible. Well, so this is exactly how we utilized and sometimes keep utilizing in-app caching techniques, relying on different local caches. But again, so it turns out to be the market, it was not enough for the market because the complexity of applications keeps growing. Our demands keep growing. And the amount of data we have to process and stores also soars. And we need to do something with that. And this is why it's around mid-200s, we could see the first distributed caching projects and products that appeared in the market. So the idea of this product was pretty simple. Let's say that why do I need to use a local cache if I just can use a distributed cache that can be reused by many applications if it's needed. And also the beauty of such a distributed caching technology is that You don't need to evict or maintain your local caches individually on every application side. This cache will decide on its own when I need to evict data, when I need to preload the new data. All these operations are outsourced to the distributed caches. And now applications can just connect to these caches and somehow to get data from there in the shared form. So, and here is what are the other benefits of the shared caches? You can go beyond local RAM capacity. In your local caching scenarios, you're limited to the physical RAM you have on your local machine. But with the distributed cache, you can have 4 machines, you can have a dozen of machines, or you can have hundreds of machines. It's up to you. And the more machines you have, the more RAM is available for your cache, the more data you can cache in RAM. And that's probably the good benefit. And here is among probably the most prominent or the most honorable caching technologies that we have in the market. We have Memcached and Redis. Actually, those products are really simple, and they do all the job that is stated by them really great. So it's good to share distributed cache. You can really go beyond RAM capacity. It's much easier to maintain it as a local cache for sure. And also it's easy to start with them. And you can work with these caches in the form as you would work with hash tables. You just need to know a key, and every key stores a unique value. Pretty simple. But also, that was not enough for developers and architects. People, for some of the use Redis and Memcache, they're really well suited for a variety and for dozens of different use cases. But at the same time, they cannot satisfy all the requirements of all the other use cases that we have in the market. And let's take a look why distributed caches, where distributed caches fail. Why we cannot just take Redis or Memcache and use them for all the caching scenarios we need. So the first, one of the main things that comes to my mind is that there is a lack of automatic synchronization between, let's say, Redis and our database, our persistence layer, such as relational database or NoSQL database. If you take a look at this diagram, here is we again have the same 2 applications that work with a Redis cluster, but at the same time, if this Redis cluster has to persist data in our database, or this cluster has to be updated with the data of this database, then you need to do this somehow manually. It's not supported by Redis or Memcache, so it becomes your burden if you want to keep your Redis cluster in the remote database in sync. And the things get worse if this database is being updated by a third application directly. What can you do with this? Because now it means that this database needs to accept changes from both your third application and from your Redis cluster that is being directly updated by first and second application. That's for sure inconvenient. And this is why Redis is not widely used for the scenarios where you want to keep both your Redis cluster and database in sync, so that the data that is stored both in Redis or Memcache and database is always in sync without any lag. And actually, that was probably one of the main reasons why the caching evolution turned to data grids. And the concept of data grids is pretty similar to the concept of distributed caches. First, I like when to call distributed cache, this data grids as distributed cache with brains, because technically data grid is the same distributed cluster that stores your data and distributes your data across all the memory you have across all your machines. It's pretty simple. But on top of this standard caching operations, such as an ability to to cache a value with specific key, ability to scale out, ability and fault tolerance. You can also get another capabilities from the data grids, such as automatic database read and write through capabilities. If you take a look on this slide, on the image on this slide, you will see that whenever you update, introduce, or bring any changes to your data grid cluster, the data grid cluster is going to push these changes to your database directly, automatically. You, as an application developer, don't need to care about that. And this is why data grids are widely used as a caching layer on top of an existing database solution or application. You just take a data grid, you just deploy your data grid on top of your database, and your application starts working with your data grid directly, and the data grid writes and all the changes to your underlying database. So you solve this problem that we had with distributed caches. With distributed caches such as Redis or Memcache, it's your job to make sure that the data in disk and RAM is synced up. On top of this integration with the databases, the data grids gave us so-called collocated processing. Collocated processing is an ability to leverage from calculations that can be executed directly on the data grid nodes. We are going to look into the collocated processing shortly in 5 or 10 minutes, but basically collocated processing can be compared to the MapReduce paradigm that is applied and adopted in Hadoop. The idea here is that instead of retrieving all the data from your cluster nodes and bringing it back to your applications, why don't we just write a calculation, send this calculation to our cluster nodes, and walk through our data, do all the calculations there. And this is how we can minimize data movement across the network. And also, collocated processing is related to other aspects of how the data is stored. we're going to review this briefly in 10 minutes. And finally, the better scalability of data grids, because it's easier to, from the architecture perspective, it's easier to scale them. And it's easier to make sure that your solution will be highly available. But the data grids also, if you're looking at this diagram, we can assume that, wow, then this should be enough. Okay, so now I solved 2 problems that I had in my architecture that I wanted to support. I have my applications. I can use a cluster room machine that will keep and store all the data in memory. And if it's needed to perceive this data, I can do this. I can take, let's say, a relational database, or I can take a NoSQL database, and the data grid cluster will just make sure that all the data will be persisted there. But it might be totally enough for some of the scenarios, but the market demanded additional features. And here is a list of the points why data grids fail sometimes, why data grids are not used for some of the use cases. First, even with all this simplicity and easiness of data grids-based architecture, you still have to learn a new kind of language for your data querying. Yes, you can use key value operations, such as those that you usually use with Redis, Memcache, to simple cache table. But for us who invested a lot in SQL language, it might be a big deal. And data grids usually do not support SQL. They provide some custom language for advanced queries, but it's definitely not SQL. Also, ACID transactions. Here is we're talking about distributed ACID transactions that we usually apply and execute in relational databases. Right, data grid vendors, they provide transactional support, but sometimes it's not as rich, or it's not as big as the one you can find in the relational world. Another point here is that good, we can use relational database as a persistence layer on top of the data grids, which might be totally fine for our use cases. But at the same time, the database becomes a bottleneck. Because if we remember the previous slide, with the data grid and any other distributed caching technologies such as Redis, you usually accelerate your read operations because the data is in RAM. You reading data from specific nodes. But whenever it comes to updates, first, the updates will be distributed and across the cluster of machines, but then we also need to persist the updates to disk. And if you use a relational database as a persistence layer, then here is we come to the bottleneck for our write operations, because every cluster node is going to write the changes to our persistence layer. And also the database, relational database in particular, is going to be our single point of failure. So whenever we lose any cluster nodes of our data grid, we are not going to affect our applications. Because usually you store several copies of data cluster-wide, and your applications will be just getting data from the nodes that survive. But with the database, if the database is went down, I don't know what to do. So now the cluster cannot persist the data, and we need somehow to keep in sync both the cluster and database after the latter is recovered. And final thing, if we use relational databases or NoSQL databases as the persistence layer, and by some reason we restarted our data grid cluster, we usually need to preload all the data from our database into the cluster because of the operations and queries we usually use in the data grids. And here is again, that might be a huge concern for some of the companies. Just recall how much money it cost Amazon that famous 5 minutes downtime when Amazon lost around dozens of millions of dollars just in a matter of 5 minutes because the applications were down. And here the situation is the same. If you now our applications work with the data grid directly, if you need to restart the data grid, the applications will not become operational until the data grid is populated with data from disk. And again, here is you're waiting more, and it's not that good. And actually, these disadvantages led or pushed the creation of other kind of products that appeared in the market, and those products also are widely used for the data caching and other scenarios. And here is we're talking about in-memory computing platforms. And Apache Ignite is actually one of the examples of in-memory computing platforms. So technically, Apache Ignite is a memory-centric distributed database caching and processing platform for transactional, analytical, and streaming workloads. And it belongs to the category of in-memory computing platforms. So here is on this slide, you can see that the core of the system is the memory-centric storage. So that's our distributed storage that by default and stores all the data in the indexes directly in RAM. The same way you would store data in the data grid or let's say in a distributed cache such as Redis. Also, such as any other data grid, Ignite is capable of persisting data in a third-party database, such as a relational database or NoSQL database. The same capabilities, no any differences, and the same guarantees. But at the same time, to solve the problems of the data grids or distributed caches, Ignite introduced another features to its project portfolio. So, and here is the first one is Ignite Native Persistence. Ignite Native Persistence is a part of the memory-centric architecture. It's just your disk tier. You just enable it, and all the data that you store in your cluster will be distributed and persisted on disk across your cluster machines. The same way, actually, in a similar way, in a similar concepts that the data is persisted by distributed databases such as I don't know, Cassandra, Google Spanner, and many others. So you have the whole copy of your data on disk, and you can store as much as you can in memory. So you can store the same copy in RAM, or you can store less, depending on your resources. And then on top of this memory-centric storage, we have the same API that are usually available in distributed caches or data grids, such as key value APIs. In-memory computing platforms such as Apache Ignite provides ACID transactions. And also it gives you APIs that are usually not available in data grids and distributed caches. And here we're talking about SQL or machine learning capabilities. Another player from all the in-memory computing platforms market is GridGain. And GridGain is actually an enterprise product that is built on top of Apache Ignite. So the core of this product again is Apache Ignite. So we can use Ignite, and then if we decide to switch to GridGain, we usually do this to get additional features that are built on top of open source functionality. So for instance, GridGain provides capabilities needed for data recovery, such as data snapshots. That's for the scenarios when you use Ignite native persistence. Also, you can get advanced monitoring and management tools. If you want to be sure that your cluster, your Ignite or GridGain cluster is secured, and you want to maintain some audit trails, you also can get this from GridGain. And final feature that is available there is data center replication. That is useful for the scenarios when you have several clusters deployed in different geographical regions. Okay, so that was about the evolution of caching technologies. So we started with the hardware, then we went to the operating systems with all the virtual memory page buffers and memory map files. Then we look at how local caches were applied in our applications and why the local caches boiled the ocean and led it to the appearance of distributed caches in the market. And finally, we see that distributed caches are not the end of the story. And we have two other product categories, such as data grids and memory computing platforms. And now let's briefly look into the memory computing platform using Apache Ignite as an example. And here I'm just going to look at how Ignite can be used as a caching solution on top of your, let's say, existing database. Let's say that here we have some relational database that we just already use for our application. And we just want to take Ignite cluster and deploy it in between the database and our application. Yes, it's possible to do. You just use the cluster as your main storage, and Ignite will make sure that all the changes, that the data that is kept in Ignite and database is always in sync. It's going to use so-called read-through and write-through capabilities. At the same time, you do not need to learn from scratch in terms of how to work with your data, because Ignite provides SQL engine that is NC99 compiled. You can use aggregations, joins, and many other capabilities you will find in standard SQL databases. And also, speaking about the transactions, all the transactional changes that will happen in Ignite, they will be committed to your database in a transactional fashion too. But here the database has to be transactional, right? So we are not going to deceive anyone. So if your usually relational databases are transactional, which means that all the changes that are committed to Ignite will be committed as a part of the transaction to the relational database too. But if you're using NoSQL database, no. Here we cannot beat the physics. We cannot make NoSQL database transactional. Next, a little bit more about the distributed SQL capabilities. So again, with Ignite, you can truly interact with Ignite as with a distributed SQL database. How do you do this? First, yes, you can use Apache Ignite, Java.NET or C++ APIs, or you can connect through your applications using JDBC or ODBC drivers. So if your application already uses SQL a lot, and you already rely on different JDBC and ODBC drivers, then for you it will become a matter of just sweeping at the drivers and making sure that you're not using some vendor-specific SQL functions. Because Ignite implements NC99 SQL specifications, and you can see, you can go to our documentation page to see all the details about all the functions and capabilities available in Ignite in terms of SQL. The other thing that we mentioned while we were talking about collocated processing and benefits of data grids and in-memory computing platforms is shown on this slide. The collocated processing idea is pretty simple. To the left, we can see so-called standard or client-server interaction. We have our application, and the application wants to perform some operation. To accomplish this operation, we need to get some data. And here is to the left, we see that first application requests data 1 and data 2 chunks from our cluster nodes. It brings it to the application, does something with this data. It might be it can push the changes back. And here is we need to move the data back and forth. The collocated processing takes another approach. With the collocated processing, we just work with the data as we would just create, let's say, a calculation. And this calculation will be sent to our nodes where the data needed for this calculation is located. And this is what happens on the picture to the right. There is some calculation, we just send it to the data nodes, and then if it's needed, we are getting the final result. This is how you can tremendously reduce the performance and the data movement, not the performance, you can tremendously reduce the data movement across your network. And here is I can give you a really good example on how the collocated processing helped one of Ignite and GridGain customers. That was a bank, and as many other banks, the customer maintained millions of different savings accounts. And every month, the bank had to walk through all the savings accounts and apply some interest rate. When the bank used the classical client-server approach, that would go to a relational database, take all the data from there, do some manipulations and bring it back. It would take 2 hours and 30 minutes to complete the whole operation. But once the bank moved to the collocated processing approach, the time was reduced to 10 minutes. 10 minutes over in compared to 2 hours and 30 minutes. Why? How could they do this? Simply because they, instead of bringing the data from the relational database and do some calculations locally, they just run an application. That application would issue a calculation. That calculation would go to all the server nodes, all the cluster nodes that store all the data, and all this and all the savings account will be updated locally on the remote nodes without any data movement over the network. This is how you can apply collocated processing techniques within memory computing platforms or data grids to achieve tremendous performance improvements. But the collocated processing and computations are usually available on data grids and in memory computing platforms, but collocated joins are usually provided by in-memory computing platforms such as Apache Ignite, which supports SQL in general. And here is the idea is pretty simple. Here is we need to collocate the data. In this example, we have a database of cities and countries, and we ensured that all the cities from a specific country are located on the same node. For instance, node 1 here stores all the Canadian cities on the node where the Canada's record is located. And the same is true for cities of India. And now, whenever we want to run this query with join, this query will be sent to both nodes, but the join part will be completed locally on these nodes. The nodes do not talk to each other, moving back and forth specific cities, because all the cities will be automatically stored on every node that will where the specific city is located. And this is actually how you can avoid data movement during the join time of your SQL queries, And this is how actually you can efficiently execute distributed joins, not only in products such as Apache Ignite, but also in many distributed databases such as MySQL or ODB or Google Span. And that's a pretty simple approach. You just need to make sure that all your data is collocated. And this is how. So the SQL with joins is a reality of modern world of our current technologies. So it was said before that it's not possible to execute selects or SQL efficiently, but it's no longer true. And Ignite and many other distributed databases prove this. And by some reason, if you could not collocate the data, Apache Ignite or other distributed databases, they can use so-called non-collocated joins. This scenario, by some reason, the data was not collocated according to our configuration, and we ended up having this distribution when some Canadian cities are located on both nodes, and the same is true for Indian cities. And now, whenever we execute the same query, during the join time, the nodes are going to talk to each other, moving the data back and forth just to complete the query. Yes, this will bring down the performance of your distributed joins, but at the same time, these non-collocated joins are used as your final resort for the scenarios when you could not collocate the data somehow, but you still want to execute a specific query with joins. Finally, speaking about transactions in Ignite, as I said, are distributed. We support pessimistic, optimistic, with other serialization modes. They are based on two-phase commit protocol. So, we update not only in memory, we also update the disk if you use Ignite native persistence. We keep in sync we make transactional updates for RAM on your, let's say, relational database, but also if you use Ignite native persistence, you will get the transactional guarantees across RAM and disk, because the changes and different transactional markers will be written to your write-ahead log file that will guarantee that even during the failures, the cluster will stay consistent. And finally, speaking about Ignite persistence, Ignite persistence is a part of our memory-centric architecture. What does it give it to us? And actually, these capabilities are usually not available in data grids. That another differentiator between the memory computing platform and data grids. First, Ignite native persistence stores the full set of data on disk, and that will be your active data, meaning that if you cannot feed all the data in memory, Ignite can query data with disk as any other disk-based database do. So you don't need to worry about the fact that, oh, I cannot feed all the data in RAM. What do I do? It's not a big deal in Ignite. Okay, so we are going just to query data, take the data from disk. Also, this capability of having all the data in disk allows us to restart Ignite clusters as fast as possible. If by some reason your whole cluster went down, then once your cluster is up and running, you don't need to wait while all the data is preloaded from disk. You can enable your applications and they will start working with the cluster. And the cluster will preload the data from disk on demand while you're querying it. So yes, in such a scenario, the performance will be slower if to compare to the case when all the data is already in RAM. But anyway, your applications are up and running. Your downtime is reduced significantly. Well, that's all for now. So we reviewed the evolution of caching technologies. We saw that the cache is not only about software, it's also about hardware. Now I hope that you see the difference between different distributed caches such as Memcache, Redis, data grids such as Hazelcast, Gigaspaces, and in-memory computing platforms such as Ignite or GridGain. And now, before we finish and switch to the questions and answers section, I want to quickly show you a nice demo, just 3 minutes demo, that shows how to deploy Ignite on top of an existing database. Here is I have my Postgres SQL database running. I have cities and countries tables, just cities and countries. We used this example in our SQL slides. And now I want to deploy the cluster in Ignite cluster on top of it. Usually it's easy to do. I'm going to the configuration of Web Console. Here as we're using Ignite and GridGain Web Console. Let me try to show you. I remove the previous results. I want to first import schema from my database. I've connected to the to PostgreSQL database, and now I importing schemas of cities, countries, and caches. Ignite is going the Ignite Web Console is going to prepare a special configuration for me. So what I need to do here is this whole configuration. You can just after the talk, you can just click through and play with this management tool on your own. But the whole idea here is that the configuration is ready, and we can download ready to be used project with all the parameters generated for us. So I'm preloading this project. It's over here. And just for the sake of the simplicity, I just preloaded the same project before the webinar. It's here, up and running. I just specified the address of my PostgreSQL database, credentials, and I already have here is my first cluster node running. So this node already knows about PostgreSQL database. Let me start the second node while we do this. And here is from this console, let's check it up that the cluster is up and running, that I can connect to my local cluster. Come on, okay. Okay, here is I have to my server nodes running locally on my laptop. And the next step, I want, so the cluster is empty. We have the caches, city, country language, but there is no any data. Where do we take it? We need to preload it from our PostgreSQL database. It's easy to do. So here is again, Web Console generated this simple application for us. Here is we connecting to the cluster, my two cluster nodes. And I'm just triggering this load cache methods for all the caches we have. And then Ignite will find out where it should go. So you just say, I need to preload data for this, that, and that. And Ignite knows according to the configuration that we need to use PostgreSQL. And the data is already there according to the application. Let's check it up. Okay, it's over here. We have our data. Several entries. It's some, I don't know, some message. It's harmless. And now let's try to run our first SQL queries. For instance, this SQL query will be run against the data that is in Ignite. So we're not running SQL queries over PostgreSQL. It's not supported. SQL queries in Ignite can be executed over Ignite data that is in RAM or in Ignite native persistence. But anyway, so here is we're trying to find the most populated countries in the world. We have China, India, United States. Next, let's run something more complex. That's the same query we showed on the previous slides. I want to find out the top populated cities in countries such as United States, Russia, and China. We have Shanghai, is the most populated. Then we have Moscow and New York. Also, we can do the following. Let's try to update the data. So, for instance, I have some city here from Bukhara, from Uzbekistan. That's the city's population. And now I want to update the population of the city. But before, I want to be sure that all the changes will be reflected to the PostgreSQL database too. So let me go ahead and copy paste the same query. I want to check that the data is consistent across Postgres and Ignite cluster. Okay, the population is the same. Now let's go ahead and update the record. Okay, I want to bring down the population. Okay, it was updated. Let's check it up that it was updated in the cluster. Okay, the population is lower. And what's about PostgreSQL database? Okay, good. So this is how actually write through and read through works in data grids and memory computing platform. And this is one of probably the main difference between distributed caches such as Redis or Memcache and data grids and memory computing platforms such as Apache Ignite. With Redis or Memcache, you cannot do this automatically. It becomes your burden. You just need to care about your persistence layers, such as relational database and your Redis cluster. So finally, some of the resources You can read more about Apache Ignite. The first link shows where you can find Apache Ignite technical documentation. Let me quickly switch to that slide. Sorry for messing this up. Okay, so the first link goes to Ignite technical documentation. Then we have recordings of in-memory computing essential. It's useful for those who want to learn more about how in-memory computing platforms and data grids work, different architectural decisions, how to use them efficiently, and what you need to learn if you start with them. And finally, you're comparing some capabilities of distributed caches, data grids, and in-memory computing platforms today. And for instance, if you want to learn more about the difference between Ignite and Redis, you can go ahead and download Ignite and Redis comparison chart using this link. Okay, so we have several minutes for your questions, guys. Please ask them.
All right, so can everybody hear me? Can you hear me, Dennis?
Yeah, I can.
Okay, we are getting some questions. The first one was towards the end, was can we use this console for POCs or with Ignite? And I think the short answer is just yes, just go to console.gridgain.com. I think that's right.
Yes.
And they can use that console. Yep.
Yes, you can use it for free.
So what makes an in-memory data grid scalability much easier than when you're trying to scale a distributed cache?
Yes, so here is in data grids, according to my observations, the scalability is really automated a lot. So for instance, if we take, let's say, Ignite or Hazelcast, whenever you want to whenever you want to add a new node to your cluster, you just add it, and then the cluster does the rest of the job for you. It will rebalance the data automatically. It will make this node as a full-fledged member of your cluster. In other products, and from what I saw in memory distributed caches, you need to do some extra manipulations. You need to reshard your data manually. I mean that you just need to involve some steps. So you need to trigger something and you need to wait while this happens. In data grids, usually no, it's just rebalancing happens in the background and your applications just work with your cluster like nothing had happened.
Mm-hmm. So they're doing replication at the shard or the partition level, but that's about it.
Mm-hmm.
Okay. Why haven't these caches added SQL support?
Say it again.
The question is, why haven't these caches or distributed caches added SQL support?
Because I guess they are like all the kind of caching technologies and capabilities we reviewed today are targeting specific use cases and segments. And for distributed caches, it's not needed. They found their segment, they found their customers and use cases. And for those use cases, they feel comfortable and fine there. They don't want to make their technologies probably much more complex. Because if you're going to add SQL support to distributed caches, then you're going to complicate your architecture a lot. But at the same time, the distributed caches, those usually cannot be used as solutions for mission-critical applications, such as your system of records. And data grids, or like in-memory computing platforms, such as Apache Ignite, decided, to target that group of use cases, that group of customers, those who use different caching techniques and in-memory storages for use cases when you need to have Ignite as a backbone of your mission-critical application, such as a system of record.
Mm-hmm. Another question, how do you make sure the data is on the right nodes for collocated processing and doing writes?
So here is, there are two things in collocated processing. First, we have a data-to-data affinity collocation. like as it was shown on the previous slides, it's all about configuration. Once you configure that there is some relation dependency between your cities or countries, then the data that all the cities, whenever you're going to put a new city into your cluster, it will be automatically stored on the same node where the country is located. That's done. You just need to configure your keys properly in Ignite. And the collocated processing, if you need to send your computation to a specific cluster node where the data is located, there is also a special API. You just need to say, okay, so I want this calculation to be executed where this key is located, so please do this. And Ignite will send this, route this calculation there. And if you want to learn more about the collocated processing, I would encourage you to watch the recordings of those in-memory computing webinars. The links I left on the resources slide of this presentation.
Mm-hmm. I think we have time for one more question. Caches do ACID transactions as well, right? What's the difference?
Caches what?
It says caches, some caches, I'll paraphrase it, some caches say they do ACID transactions as well. What's the difference between that and what an in-memory data grid or beyond, what in-memory computing platforms can do?
If to compare, let's say, let's probably take Redis as a distributed cache and Ignite as a in-memory computing platform here. Redis, right, they say, and they do support transactions, but those are local transactions, meaning that they can be executed only on a single Redis shard.
Mm-hmm.
So if you want, let's say, to move money from one bank account to another, and if both accounts are stored on two Redis shards, you cannot do this, because Redis just executes transactions only in the process of one shard. With Ignite, there are no limitations. You just start your transactions. If, let's say, two deposits are located onto different nodes, it will be committed successfully or rollback if it's needed.
Okay, and optimistic or pessimistic?
Yes, so, and ACID is also about different, it's all about choices. It's about not about only, pessimistic transactions. ACID also provides you optimistic guarantees, or you can use serializable read committed or repeatable read transactions, all sort of different configuration options.
Okay, perfect. Well, that was pretty much all the questions, or at least all the time we have for questions.